We're going to begin with right triangle ABC. B is the right angle, and then AB is the shorter leg, BC is the longer of the two legs, and AC is the hypotenuse. And I'm going to draw the altitude to the hypotenuse. So that means that we're going to go from the vertex that is the right angle and draw a segment perpendicular to the hypotenuse. So like this. And then this is by definition a right angle. So we have a case like this. What we can notice, should notice now, is that we took our original triangle and we've divided it into two separate triangles. And the original triangle was a right triangle, and now these two other triangles, we'll call this one the small one and this one the medium one, they're also right triangles. If we look at the smaller triangle, let's call this point D. If we look at the smaller triangle now, we can see that it has a right angle here from the altitude and contains angle A. And the entire triangle has a right angle here and contains angle A. So the smaller triangle and the whole triangle are both similar to each other by angle-angle similarity. Again, because they both have a right angle and they both have angle A, which is congruent to itself reflexively. So we can then say that triangle ABC is similar to triangle, and now make sure that I get the correct correspondence. So A is the larger of the two acute angles, B is the right angle, C is the smaller of them. Well, I know A corresponds with A. In the smaller triangle, then the right angle is at D, and the smaller triangle has A, D, and B as vertices, so the remaining vertex has to be B. That means that this angle in here, angle ABD, is congruent to angle C. We could do the same thing looking at the medium triangle. It has a right angle where the altitude is and contains angle C. And the whole triangle has the right angle at B and contains angle C. So those two triangles, the medium one and the whole triangle, are similar by angle-angle similarity as well. So then we can say that triangle ABC is similar to triangle, let's see here. Well, C, I know, corresponds with C, so that'll be the last letter. B was the right angle. In the medium triangle, D is the right angle, so we'll put that in the middle. And then that only leaves B as the third vertex. And by the transitive property, then I can say that all three of these triangles are similar. So triangle ABC is similar to triangle ADB, which is similar to triangle BDC. So all three of these triangles are similar, and that tells us then that all of their corresponding parts are proportional. And these proportions are the part that end up being interesting in this. What we're going to do is deal with special cases related to when the altitude is drawn to the hypotenuse of a right triangle and the similar right triangles that are created. So the first set of proportions that we're going to do is by comparing the shorter leg to the longer leg in each of these three triangles. If this is an isosceles triangle, then we don't have a shorter leg and a longer leg, but then a lot of the ratios end up simplifying down and aren't as interesting maybe to us, or not as generalized. So I'm going to compare in each of these cases the ratio of the shorter leg to the longer leg. And that means in the whole triangle, that's side AB is the short leg and side BC is the longer leg. And I know that these things are proportional, so then I could look at the smaller triangle and say that its shorter leg, which is AD, to its longer leg, which is BD. This is equal. And since we have three similar triangles, we can write a proportion with three equal ratios. So lastly, we have the medium triangle, which then the short leg of that is BD, and the long leg of that is DC. DC. So what's noticeable in this, what stands out to us, is in this part of the proportion where we have the same side in the means positions. and then we have these other sides in the extremes positions. But this is an example of where we have a geometric mean, right? And the side that's in the means position here is this altitude, is BD. And the pieces in the extremes positions are AD and DC. So if we look at this in terms of what's happening in the triangle, what we're finding is that the altitude is the geometric mean of the two pieces of the hypotenuse that it's divided into. We can say that we've got the way that we traditionally write our geometric mean. We have A to X is equal to X to B. And we've seen that this solves down to, or simplifies to, X equals the square root of the product of A and B. So now, if we have a problem like this, where we're given these different pieces, if you provide any two of these three pieces, we can identify the third. And that's one of the cases that we look at with the altitude drawn to the hypotenuse and the similar right triangles that are created. There's another relationship that we'll look at in just a moment.